As humanity responds to the global climate change crisis, robotics and autonomous systems for the inspection, maintenance and repair of net zero energy generation infrastructure is increasingly viewed as a vital enabler in the energy transition.
In the management of complex infrastructure offshore, there are challenges such as workforce resilience, cost reduction, life cycle decarbonization, and safety for human operators in dynamic and remote operating environments.
Autonomy in inspection, maintenance and repair missions demands robust operational governance. This is especially important when operating in dynamic environments, alongside a diverse range of functionalities and capabilities tailored to specific assets and operational environments.
Currently, robotics and autonomous systems are predominantly focused on individual or multi-robot platforms for specific short-term inspection, maintenance and repair activities in relatively controlled environments, all of which require a dedicated team of deployed human assistants.
In the evaluation of our Symbiotic Multi-Robot Fleet, we utilize an offshore substation analog as displayed, which has several areas of corrosion for inspection on an offshore asset.
Our laboratory was made to represent a cluttered area, representative of the operational area where a Symbiotic Multi-Robot Fleet, or SMuRF, is deployed to complete a confined space inspection mission. In our mission evaluation, the SMuRF is deployed autonomously via a quadruped, wheeled robot, UAV, and infrastructure monitoring systems and are designed to cooperate, collaborate, and corroborate, what we call C3 governance, in partnership with a remote human-in-the-loop operator.
The orchestration of our Symbiotic Multi-Robot Fleet is implemented via our Symbiotic Digital Architecture that permits near to real-time C3 governance for up to 1,600 distributed robots, sensors, and assets.
The evaluation of our SMuRF is characterized by its ability to respond to randomized reliability, safety, and resilience mission variables.
At this point, we can see the Operational Decision Support interface, which allows for the human-in-the-loop to observe and interact with the orchestration of the SMuRF and environmental monitoring systems. The Symbiotic Interaction Speedometer enables for qualitative analysis of data being shared across the SMuRF. For example, currently the Spot and Husky colour-coded needles match as they are both sharing diagnostic data to the interface. However, the Spot needle will soon increase when the autonomous mission starts.
At this point, the Check All Rooms button is pushed for the Spot robot to initiate the first autonomous mission. In the message box, we can see that the autonomous mission has started. However, the Spot robot requires time to complete the initial boot sequence.
The Husky focus area features the diagnostic information including battery charge, voltage, and the current of the motors. This allows an instant overview of the status of the robot.
The Spot focus area includes similar diagnostic information on the status of the robot.
The Take Control button enables for remote teleoperation of the DJI Telo UAV via the interface, allowing the human operator to gain an improved understanding of the inspection area. As we move back to the Operational Decision Support interface, we can see that the Spot has begun the first autonomous mission. Footage within the interface is being displayed from security cameras within the laboratory. Under normal operating circumstances, each robot would not normally come into such proximity, but the practical realities of operating offshore means that the luxury of separation does not exist in the confined spaces typically found on the offshore installations or within complex structures. These factors have the potential to result in navigation conflicts between robots.
For the self-certification of autonomous systems, the dashboard utilises a set of rules which is informed via our designed reliability ontology.
Next, an overview of Spot's mission is displayed through the corridor, where the fiducials are used in the autonomous navigation of Spot via the Boston Dynamics Software Development Kit.
A quadruped is a vital robot for inspection missions within a SMuRF, due to its ability to traverse over terrain which a wheeled robot is unable to.
Following this initial mission by Spot, 3 robots are deployed to evaluate a large area for corrosion, which can be classified using ISO standards as Category C5 or CX. Displayed is a visualization of a corroded area which requires inspection from a range of robots at varying heights, in addition to difficult to navigate areas. This is why we use a multi-robot fleet, as each robot leverages the capability of others to complete an holistic assessment.
This is a good moment to point out the lay-by zone which Sport returns to, following the inspection for corrosion. This is a predetermined safe area. The lay-by zone has a key advantage in that the robot can fail gracefully when a fault threatens the mission, preventing loss of the asset.
For the multi-robot inspection mission for corrosion, firstly, the multi-robot button is activated from the interface. This initiates the missions for all robots simultaneously. Husky moves into position to complete an inspection of the right side. Spot moves into position to inspect the left area, and the Telo UAV completes an autonomous inspection of the difficult to reach areas at height.
Following the corrosion inspection, Husky moves to the wind turbine blade for preparation to inspect for subsurface defects. Husky has a non-destructive, non-contact millimetre wave radar on the left robotic manipulator arm, which can be used for inspection of surface corrosion and surface and subsurface inspection of wind turbine blades. This sensing mode is low power, tunable, and can be easily integrated with robotic systems.
The simulation ghosting function is used to ensure the Husky robot arms are programmed to move to the correct position for inspection of the wind turbine blade. Once this virtual simulation is approved by the human in the loop, it's applied to the real-world robot. For this scenario, an error is returned to the Operational Decision Support interface stating a battery fault. This is where C3 governance and symbiotic interactions are central to resilience and reliability.
The Telo UAV is programmed to ascend to complete an autonomous mission to identify if there are any visual problems on the Husky robot. This is verified via the human in the loop having the ability to access the UAV camera.
Due to the nature of the fault detected on board Husky, the interface activates a predetermined mission on the Sport robot to move into position to collect a battery from the stores area. The Sport then collects the battery autonomously and moves the battery to the Husky robot, which rectifies the battery status.
Let's reiterate the autonomous nature of this decision for Spot to support Husky, which is not hard-coded to occur and is dependent on certain mission parameters and conditions not being met. In this case, a battery warning fault which needs rectified. We utilise machine learning algorithms to detect the battery pack and Husky robot sequentially to complete the objectives of this mission.
In future demonstrations, this symbiotic interaction may represent robots sharing tools, supporting or corroborating inspections, performing material logistics during repair, or allowing for an improved operational overview for a human in the loop.
The future SMuRF consists of a cyber-physical system which allows for scalable autonomy via Autonomy as a Service. An increased operational overview of assets, systems and sensors is achieved via digitalization. Symbiotic interactions can take place autonomously across a SMuRF to increase safety, resilience and reliability.
Robotic platforms each have their own strengths and weaknesses. Therefore, the SMuRF allows for the leveraging of capability across a team of cyber-physical systems.
To ensure the resilience of autonomy, other robotic platforms can be used to assist each other in the completion of tasks in the future.
A future visualization of a SMuRF in an offshore renewable energy context is displayed, which visualizes the multi-robot fleet, environmental sensors and offshore wind farm assets under the SMuRF architecture to enable for increased symbiotic interactions.
The Symbiotic Digital Architecture created is platform agnostic, allowing for several types of platforms, programming languages, proprietary systems and sensors to be included within the SMuRF. Please see the following publications and GitHub repository for more in-depth information on the topics covered in this summary video. We also welcome any collaborations in the future where our primary work is gauged towards offshore, renewable energy and robots for nuclear environments.